Hello and welcome to another session of classical motion of a single particle. Here in this session we just continue our previous discussion on motion under a central force. So, as I said that whenever a force has this specific form of Fr r cap, then according as this Fr is greater than 0 or less than 0, it can be repulsive. So, greater than 0 it is repulsive, and less than 0 it is attractive. Then this has very interesting properties. This is curlless, this is conservative, the total angular momentum is conserved or is a constant vector. Okay. The motion under a central force takes place in a plane, in a 2D plane or in a plane, of course, in a plane. And which is the plane? The plane is perpendicular plane to L cap vector, that is the direction of the momentum. So, let us say if the particle is moving, for example, in such a plane like this, then the momentum vector will be exactly this, perpendicular to this. Okay. Then r cap can be actually in anywhere in this plane. Okay. R cap may be here or here, but it will always be confined in this plane, so that r cap dot L cap is always 0. Okay. That we have to maintain. We calculated the radial and the cross radial components of the acceleration, and then we used our famous Newton's laws, means 2D polar coordinate form, and then we equated m, we just simply said that m a r is equal to f r and m a theta is equal to f theta. They are just the radial and the cross radial component of the force, and they are the radial and the cross radial component of the accelerations. Then finally, we have actually shown that the whole system of equation becomes like this: m r double dot minus h square r cube is equal to f of r. Now, here at this point I want to mention again a point of caution, that is, it is true that when the motion is taking place under a central force, the motion is confined in a plane, and then under that condition only, when you have this specific structure of the force, you have this cross radial acceleration is equal to 0. However, you can encounter a condition in which the motion is taking place in a plane, but the force is not necessarily a central force. Try to understand. If the force is central, the motion is confined in a plane, but if the motion is confined in a plane, the force not necessarily is a central force. Okay. Actually, you can see several examples like that. Okay. And if this is the case, then basically you do not have these two equations to be true like this, and for that you please remember that whenever this second equation is 0, then only you can write that as m, this is equal to m by r d dt of r square theta dot is equal to 0, and from that r square theta dot equal to constant. However, if your motion is planar, but the force is not central, then this conservation quantity is not guaranteed, is not obtained, because this one will then be not equal to 0. However, here again I am just putting this to be equal to 0, so that we retain our case of central force. Okay. Now, you see that at this point we will do something very interesting. So, we just saw how the equation of dynamics look like under the action of a central force. Okay. So, if you give me now the law of force, okay, I can actually have to solve a second order differential equation for this, for r and I can find r as a function of t and r dot as a function of t. Okay. Now, you can say what about theta, theta dot? Okay. Once you know r and since you know h is a constant of motion, so you can actually determine that from the initial conditions, that you should never forget. Okay. So, initial condition will give you h, and from that if you know r you will have theta square, and once you know theta square you can calculate theta, and then you can again by integrating you can calculate theta as a function of t. Okay. So, although finally it looks like it is a motion of r, but finally it is always when you solve, since it is a 2D motion, you have to come with as a solution r as a function of t, theta as a function of t, r dot and theta dot as a functions of t. Okay. That will complete the story. Now, one can be interested to know in this plane which type of trajectory is followed by such a particle which is moving under a given law of central force, okay, or I mean let us say an arbitrary law of central force. For those what we have to do, we have to just find the relation of r and theta, okay, or we say that orbit is nothing but r as a function of theta or theta as a function of r. Okay. So, just exactly like in an xy plane, orbit is nothing but a function, I mean having the constraint relating x and y. Let us see, if you say that in an xy plane x square plus y square is equal to constant, you know this will be a trajectory of a circle, okay, just like this. Okay. So, I will first do something very simple. So, before even going to the general treatment with the orbits, I will first take this equation, this r double dot minus r theta dot square r cap plus 2 r dot theta dot plus r theta double dot theta cap is equal to, I will say, f r cap. Okay. I will now just try to see which type of feature a circular orbit can give. So, for example, in a 2D plane if you have a circular orbit, so I can now write for circular orbit r is equal to a is equal to some constant, that is the modulus of r vector, and r dot is equal to 0, r double dot is equal to 0, but not r vector dot is 0. Okay. That means that r vector dot is not equal to 0 vector. Okay. It is only their magnitudes are constant and they are constant, and that is why their derivatives, okay, they are also identically constant. Okay. If you have this, then you also know that v, which is now is equal to, so what is velocity then? So, it is r dot r cap plus r theta dot theta cap, and in a circular orbit this is 0. So, you only have this part, but r is now a. So, it is a theta dot theta cap, and that is why in a circular orbit you will see v is exclusively along theta cap direction or the tangential direction. So, if you have a center and a particle is moving like in a circle, okay, so the velocity is always, I mean, tangential. So, that is the r cap direction is OP, and this is the theta cap direction. Okay. So, you see this all things can be rederived, I mean recovered, the things which we experience every day. So, for example, the motion in a circle can be easily recovered from this type of formulation, because this is quite general. Okay. Now, also we know that theta double dot is 0. Why is that? Because this is because theta dot, which is h by r square, is now constant, because h, this is now has become h by a square, okay, and that is why theta double dot is 0. Theta dot is not 0, it is a constant, but theta double dot is 0. Okay. So, it simply says that a theta, okay, the acceleration in the theta cap direction is equal to, so r dot is 0 and theta double dot is 0. So, a theta will be 0 and what will be AR? AR will be r double dot is 0, but r is non-zero, theta dot is non-zero, it will be simply minus a, theta dot is h by a square. So, theta dot square will be h square by a to the 4, so it will be minus h square by a cube. So, finally, you will see that the acceleration is only radial, but this is minus h square by a cube, which is negative. That means that the acceleration is radially inward. So, radially inward, and that is the only surviving component of acceleration. And that is why we say that whenever a particle is moving in a circle, okay, it has only acceleration which is along and actually in a central force. So, the particle is moving in a circle under the action of a central force. It must have only one part of acceleration, and that is this part, which is known as the centripetal acceleration. Okay. We are now going to attack a very interesting point. Okay. So, that is one point is also you can always understand that since this acceleration is negative, then this force function, which is now will be minus m h square by a cube, will also be negative, and that actually says that under a central force a circular orbit is only possible if the force is attractive in nature. Okay. So, circular orbit is possible if the force is attractive in nature. Okay. So, I mean, before just going to this general treatment with the orbits, I just want to make you another point is that what I can give you a suggestion as a very small and interesting exercise is that now you just try to understand what happens if a particle under a central force, okay, draws a straight line. Okay. So, how would be a straight line in a 2D plane, and different type of straight lines can be possible. You just take any of the straight line which you like and you analyze the motion right from the equations of dynamics for that. Okay. So, actually for deriving a general expression for obtaining the trajectories, what we will have to do is the following, that we have this dr dt and d2r dt2s in the equations of dynamics. So, they are in the equations of dynamics. To obtain orbits, we have to obtain dr d theta and d2r d theta 2. Okay. And we have to actually obtain dr and finally substitute them in the equation of dynamics. Okay. So, what is the way to go? Of course, you know dr dt will be equal to dr d theta dot d theta dt, and that is nothing but, so d theta dt is theta dot dr d theta, and theta dot, you know, we have the famous equation here which we will use always, h square theta, sorry, r square theta dot is equal to h, which is constant. So, theta dot will be h by r square, it will be h by r square dr d theta. Okay. And clearly the same way you can also write d2r d theta 2, which will be d dt h by r square dr d theta. Then you can write d d theta h by r square dr d theta times d theta dt. Again d theta dt is theta dot, which is nothing but h by r square. This is the routine work you have to perform at every step. So, it will be h by r square d d theta of h by r square dr d theta. Okay. And finally, you will see that you will have h by r square d2r d theta 2 plus dr d theta minus h by 2h by r cube dr d theta. Okay. So, compacting everything, I can write h by r cube h by r square d2r d theta 2 minus 2h by r cube dr d theta square. Okay. So, now we will simply substitute this expression to the equations of dynamics, and we will find the equation which will be very appropriate for obtaining the trajectories under a central force law. Okay. But you see already from your common sense that this equation will involve terms like d2r d theta 2 dr d theta whole square. So, it will be a second order ordinary differential equation with non-linearities, and solving such equations are not very easy, and that is why we will in the next lecture we will actually put that all the terms in the equations of dynamics, and we will somehow present the equation, and finally we will show you a way out which is much more easier, and where you can have a better way to find the trajectories given a law of a central force, or you can find the law of the central force given a trajectory. Okay. Thank you.